relativistic class, and I'd like to thank the organizers for inviting me to talk about this. So what I want to talk about is the relativistic distorted wave calculations and trying to approximate the accuracy of these calculations. I should say that a lot of the work has been done by my own graduate students and a lot at the University of Torquay, well, it's now called Indian Institute of Technology at Torquay, Reggie Sebastin and his students. So first of all, just a bit of background. Here's the formula. It's a standard formula for a distorted wave approximation. We have the final state. We have an initial state with an anti-symmetrization operator and the potential, the interelectronic potential. The difference is that here, although we write the distorted waves in the usual way, phi is in fact the relativistic Dirac-Fock wave function, configuration wave function. So we use that. It's a relativistic version of it then. And we use the graphs program to calculate these things. And the graphs program is capable of doing very elaborate calculations and putting in lots of correlation if you put in a lot of configurations and so on. So the distorted waves themselves are solutions of the Dirac equations again, so relativistic. The distortion potential is usually the one that's the upper, chosen as the static potential of the upper state. That's not always true. Sometimes for excited states, we use the lower state. And we do include exchange here in a non-local way. So we put in exchange by anti-symmetrizing the wave function. Now, I should emphasize that the exchange here is different from the exchange here because the anti-symmetrizing operator, of course, allows for exchange of the incident electron with the round atomic electron. And so they're different, I mean, in the sense that the exchange is in there twice. As I said, V is the interaction potential between the incident electron and the target. So how do we solve these things? And I wanted to spend a little bit of time talking about some of the numerical methods because I think it's important to try and make sure that we do have accurate results. And so we actually solve these things in the integral form. Now, in fact, the Dirac equations, as you probably know, are two first-order differential equations, and a lot of time physicists don't know how to tackle this. They actually convert it to a Schrodinger type equation, which is a long way around because you end up with messy potentials. But in fact, it's easy enough to solve numerically these forms of the Dirac equation. But in fact, by converting it to an integral form and this zero solution, if you have no potential or just the usual spherical spherical Bessel functions, you can get away with a larger step size. I mean, what you're doing is integrating rather than approximating a derivative, and so of course integration is much more stable, and therefore we can do that with a larger step size and rather than solving these things directly. Exchange, as I say, is included by anti-symmetrization of the total wave function. So again, in the T matrix, we have non-local potential terms coming in. For the three waves, we have the non-local potential terms coming in. Now, the other thing that I wanted to emphasize is how we do the integration in the T matrix. If you go back to the T matrix, oops, sorry. Oops. If you go back to the T matrix and forget about the A operator, you see you have two free waves here times this potential. So of course, what this will give you is a integration of two oscillating waves times the potential. And that goes on forever in the oscillator, and so there's cancellation and so on. So how do we get around that? Well, there is a method. It's not ours originally. But once you get into the asymptotic region, that is when the bound states are zero, you can go off into the complex plane and do the integration along the complex axis, the vertical axis rather than the real axis. And that has an exponentially decaying part. And so you can get away with Gauss integration with 7, 10 points, something like that, and it's highly accurate. So and this really, again, is not specific to this method. It works in general. It was originally done by Sillon and Seaton many, many years ago, but it's probably not as well known as it should be. Anyway, we've written it up in Parcel et al. Why relativistic? Well, originally we were more interested in things like spin-dependent processes and correlation. And of course, with the Dirac equations, you have spin right there, so you don't have to do any recoupling and so on. But what we're talking about today, of course, is not that. It's about trying to get decent cross sections. And in this case, what we do get from the relativistic formulation is target wave functions that depend on J. Now, J is the label that labels the different fine structure states. So we get target states with different fine structure energies. And this also has an effect on the magnitudes and the energy variations of the transition. And so rather than simply a S to P transition, we have a J to J prime transition, and the relativistic distorted wave gives you very different magnitudes and energy variations, as I will point out. The other thing that's important, as we'll see, is that if you go to the NIST tables, for instance, and look up the oscillator strengths, then there are oscillator strengths there, dipole oscillator strengths there, for transitions between fine structure states. So in other words, as we'll see, that's important, and we can then do an elaborate comparison of oscillator strengths, not simply a S to P transition, but a J to J prime transition. So it's a distorted wave method, which means it's first order theory. We have an excitation from an initial state with J and L, J being the total, including the spin, angular momentum, to some final orbital. And what we need here for the direct terms, that is where the anti-symmetrization operator is essentially 1, is this parity condition. And that's the same as is the case for non-relativistic ones. So that is the L prime plus K plus L must be even. L and L prime are defined up here. K is the order of the multiple term. In other words, if you expand the interaction potential into multiples, then K tells you which multiple you've got. As well, you must have these triangular inequalities in order to get a non-zero direct term. That is the total angular momentum of the initial state, K, and the final angular momentum, total angular momentum of the final state must satisfy the triangular inequalities, but also the actual J values of the electron that's making the transition must satisfy these as well. So we have these conditions that will determine whether or not we have a direct term. The other parts of the T matrix where the anti-symmetrization operator is not 1 will give you exchange ones, and these are always non-zero. You can always get them because you've got waves that go out, free waves that go out, and you can and they're connected with the bound state, so you always can get non-zero terms.
Well, the parity condition, what about the parity?
Well, that is the parity.
Yeah, but so it wouldn't be non-zero in that case.
Yes, it is, because you've got all the partial waves going out. It's not a simple situation like this. It always gives you a non-zero term. It's small, but it's non-zero. Well, let's take a look at dipole allowed transitions, which are the most important ones, and that is k equals 1. And so if that's the case, then the initial and final states must have opposite signs of L. In other words, they have opposite parity, and you get the final J must be equal to J minus 1, J plus 1, provided they're both not 0. And it then means that the integrated cross-sections for higher energies go off as ln E over E, so the usual sort of behavior. If we have another case where k is not equal to 1, but direct term is non-zero, then the integrated cross-sections go off as 1 over E for high enough energy. If there's simply exchange excitations, then they tend to go off as 1 upon E cubed. This is not exact, but it's something we find that seems to be the case. That's the kind of behavior you get there. Now, let's take a particular example. I'm using argon because there's good data, experimental data. And so we're going to do the 3p6, that's the ground state, to 4s state. So this is the first excited state. So we have J equals 0, it's a closed shell. Because we're exciting a p electron, J is, L is 1, but then J is a half or 3 halves, depending on how you take the spin. So that is, the shell is already split into two different cases. And the final state here we'll have J, yes, so the final state will have L equals 0, and J prime equals a half. And that gives you J values here. 0, 1 happens twice, and 2. That is, we're coupling the J here and the J here, so you get 4 different states. The J equals 1 gives you allowed transitions, allowed excitations, so K equals 1. The J equals 0 or 2 gives you exchange excitations. These are the metastable states. So if you excite the 4s level, 4s state, there's 4 levels. 2 of them are metastable. 2 of them have allowed transitions to the ground state. And the thing to point out here is that LS coupling is not valid even for here. This is quite a light atom. But if LS coupling was strictly valid, then one of the J equals 1 states would be a triplet. And, you know, the ground state's a singlet, so triplet, singlet, not allowed. But that's not true. You do get a strong transition between the J equals 1, which is really what is normally called the triplet state, and the ground state. So there is mixing even at this stage of the game. And of course, the relativistic calculation will do this to you automatically. You don't have to worry about it. It comes out of the wash in a sense. So let's take a look at a typical result here. What we have is a excitation of the singlet P1. There's a differential cross-section and the scattering angle. So I'm going to talk about differential cross-sections, although the interest I know is integrated cross-sections. And first of all, it's quite large, although this is 10 to the minus 18. It goes up to over 100 in these units. It's got a log scale on it, and this is important in the sense of trying to make sure that you understand what's going on here. Its log scale is misleading because it gives you the wrong impression. But it is an allowed transition, and so it has this typical forward peak, and more or less a linear fall off here, and quite a high value here. Well, let's then look at the next one, which is the triplet P2. So here is a metastable state. So we know for sure that it's not a direct, the direct term is 0. It's an exchange reaction. Look at the size and the shape, quite different. Still a log scale, but where the peak was over 100 here, it's now down at 0.1. So huge difference. And of course, it doesn't have that typical shape. In fact, it drops down as you go to the origin. But this is the wrong way to look at it if you're talking about integrated cross-sections. Because what you do when you integrate that is you, first of all, it's cylindrically symmetric, so you get a 2 pi, but then you multiply by sine theta. So sine theta knocks the zero energy thing, zero angle down to 0. And what you get is a peak here in the forward direction still, but it's much lower. It's only got about 10 here. And now you've got a linear scale, not a log scale. And look at out here. Well, there's not much out here. Most of it comes from this peak in here. So what about the exchange transition? The same thing here. We multiply by sine of the scattering angle. We get, again, the linear scale. We do get a peak, but it's much broader. And the part out here is a non-trivial part to the calculation. So what we've done is we've gone back here and essentially looked at what the contribution is from this peak region, because I want to argue that that's the important part, to make sure you get it correctly. And so when this peak region essentially comes down to where it starts to level off, we stop the integration there, compared it to what we get if we do the whole thing, whole angular range, and this is what we get. So here are the 4 levels of the 4s state. Here's 3, 30, 50, 100 eV. And what we get here for the integrated cross-section at 30 eV, well, they're not really that different. These are smaller, no doubt about it, but not by a huge amount. On the other hand, if you do the integration up to 30 degrees here, you get only 20% of the total for the metastable states, but here you get much larger values. If you go to 50, it's even more pronounced. Here we only integrate up to 24 degrees, and what we get here is a similar amount for the metastables, but now much higher value. And look what's happening. These cross-sections are dropping off much more rapidly than this one. This hasn't dropped very much at all. This one's dropped by almost an order of magnitude, and similarly here. If you get to 100 eV, same sort of picture. These are really small. This hasn't dropped very much. And again, most of the cross-section comes from that forward region. Let's do another example here, because I think it's important to show that you have to be a little careful about these things. Let's excite the 4p state of argon. In this case, we have the same values of the initial state. J equals 0. I didn't put it well, it's down here. But the final state now, it's a 4p electron, so it's got a half and 3 halves as well. L prime is 1. So the final values of J, there are actually 10 of them, but they cover the range from 0 to 3. But from the parity condition, because both L's are 1, L prime plus K has to be even, so K has to be even. And so what we get here are J values of 0 and 2 that are the bigger contributions because they have the non-zero direct term. And the J equals 1 and 3 are the small ones, they're the exchange ones. So this is different than it was in excitation before us. So one has to be careful about this to make sure that you do get the correct terms involved. So here is, again, a lot of numbers. I don't particularly want to go through them in general, but here's the energies again, 30 to 100. Here's the various levels, 10 of them, and we have J equals 0, 1, 2, so on. So here again, at 30 eV, they're not that much different between the various cross-section values. But by 50, these are starting to drop off, these ones with the odd values of J. And by 100, they're really small. Whereas the other ones, the ones with the direct term that's non-zero, are much bigger. They drop off much more slowly. So that's another indication there that even though in this case it's not an allowed transition in the strict sense, there's still a big difference between those transitions, those excitations which have, in this case, an even J and those which have an odd J in the final state. Okay, well, the idea is to try and assess the accuracy. And if we take a look at go back and think about the shape of this, then it's different, of course, between whether it has a non-zero direct term or it's an exchange excitation. And as I pointed out, this differential cross-section for direct excitations has a large peak in the forward direction. So it's like the Born approximation that way. And it contributes almost all of the integrated cross-section. Now, the Born approximation, of course, doesn't do very well at higher angle if we're looking at differential cross-sections. But in this case, it doesn't really matter if you're integrated interested in integrated cross-sections. And it's well known that the value at 0 degrees is proportional to the oscillator strength for that transition. You can certainly in the Born approximation do this. So here, if we take a look at the exchange excitations, they're quite different, as I pointed out. They're flatter in the forward direction, and maybe decrease there. And we get a contribution to the integrated cross-section from all angles, not just the forward peak, but there's significant contributions from the whole angular range. So in other words, if you want to get a good integrated cross-section here, you do have to get accurate values for the differential cross-section over the whole angular range. So what this means is that we need wave functions for the band state that produce accurate oscillator strength. And if we do that, we should get a good value for the direct, for the integrated cross-sections for direct excitations. So this is the primary condition. If you look at these things, the graphs code, for instance, will produce these things for you. You just have to look at the output, and you can compare them with the NIST tables, for instance, or even more accurate calculations. And you can put in more correlation, more configurations until you get decent oscillator strength. So there's really no limit here to what you can do in the graphs program. Now, there is no such connection in the case of exchange interactions, exchange excitations. But we're going to assume that if you get good oscillator strength for direct, and particularly allowed transitions, then essentially you got the same wave functions come from the same calculation. So we're going to make the assumption that the accurate wave functions for the direct term will also produce accurate differential cross-sections in these cases. Now that's maybe a stronger statement than is warranted, but let me show you some results. So here's the case we've already looked at, argon singlet P, and here's some reasonably recent measurements from a cruise group down in California. And we're back to the standard way of looking at it. And you can see here that the agreement is really quite good until you get to about here. And then there are some differences. I might argue the experiment doesn't look too good there. But it doesn't matter, because this is out here at a much lower magnitude. So what happens out here really isn't important. It's what happens here that's important if you're looking at the integrated cross-section. So here we have what seems to be, good values here. They're not exact, but they're certainly within the error bounds, and it looks pretty good. If we go to the exchange transitions here, well, it's not bad, but it's certainly not as good as the direct ones. Again, this is a log scale, so this is a factor of 2 difference there at the peak. And of course, you have to get it correct all the way out. Now, I don't know what happens out here experimentally, but assuming that this is reasonably accurate, we do get reasonable shapes, but the magnitudes are certainly different. As it turns out, the difference here and the difference here cancel one another out, so it actually does get a good integrated cross-section, but that's a bit of an accident, and I wouldn't claim that this would happen in all cases. So, as I said, just to reiterate, accurate oscillator strength will produce accurate integrated cross-sections if we're looking at direct excitations. That is the case where the direct term is non-zero. The integrated cross-section for exchange excitations are generally less accurate than for direct excitations, but we expect if you get decent oscillator strength, then that is some indication of the goodness of your wave function. So we would hope that these are reasonably accurate, although, as I said, probably not as accurate as the ones for the direct one. Okay, well, how do we judge? Thank you. Well, the one way is just to look at the NIST database, because it's got a huge set of tables for allowed oscillator strengths. So you can go there and you can look at those things. They're experimental. The accuracy limits are fairly large on those things. But there's a lot of them, because they give oscillator strengths for all transitions, for the fine structure states of the excited states to all of the lower states. So you can look at a lot of these things. It's not a simple average. It's a lot of detail here that you can look at. So that's a good way of doing it, although, in fact, as I say, the error limits are fairly large. Well, what happens if we don't have an allowed transition, if we're looking at the ground states at the P level? That's not an allowed excitation. Well, one can always look at the case where you throw in the 4s orbitals. So when you're doing this grasp calculation, you can put in whatever you like in the way of target orbitals. So you can do at the same time the ground state, the 4s levels, 4p levels. And then you can look at the oscillator strengths from the ground state to the 4s and from the 4s to the 4p, and look at all of these things. And there are 32 of them. And in fact, they do almost always fall within the error bound specified, although as I said, they're relatively large, 25%. Nevertheless, even for a simple calculation like this, where all we put in are these states here, you do get quite a reasonable value for the oscillator strength in almost all cases. So what I'm saying is that the relativistic distorted wave method is capable of producing accurate results at medium to high energies. Now, I didn't really define this before, but we don't claim that it's going to work near threshold. What do I mean by medium? Well, several times the excitation energy. So, say if we're exciting a ground state of argon, we're talking maybe 25 eV, 30 eV, something like that. Above that level, and if you get good oscillator strength, you should get good direct excitation, integrated cross-sections for direct excitation. Exchange excitations are somewhat less accurate, but again, the integrated cross-sections are more reliable in general than the differential cross-sections. So even though you might not get as good a value for the differential cross-sections, you should get a reasonable answer for the integrated cross-sections, again, provided that the oscillator strengths are reasonable. Well, the relativistic treatment is important in this case because not only does it give you different states, different levels, different cross-sections, but it also gives you different oscillator strengths. And the oscillator strength that is important here is in fact the one that corresponds to the length formulation. It's called the Bushkin formulation in the relativistic case. And that's what you need to get accurate if you want an accurate cross-sections. Of course, this isn't the only criterion you can apply. I mean, there are many other things. There's a question of whether you get agreement between length and velocity form. And we do, although, again, it varies a certain amount. There's a question of how accurate the energies are. That's important, but you can always use experimental energies in your calculation if you want to. There's the question of whether the fine structure states are in the right order. In other words, if you look at the energy levels of those, do the fine structure levels correspond to the energies in the order of the energies? And you can look at the actual splitting there, and we do get quite reasonable accuracy there. Although it depends again on how you look at the differences, whether you look at the absolute difference, which is quite small, or the relative difference, which can be quite large. But in any case, we do get quite good results with relatively little in the way of calculation. The last thing I want to point out here is all of this doesn't take much time on a computer. The GRASP program will run in a few minutes. The big problem is getting it to converge to a reasonable answer. So you run it and you look at the results and you maybe don't like what you got, so you try something different or different configurations. So you try it again, and you might spend a few hours doing this, but it's a one-time calculation in the sense that once you get them, you've got them. The other thing is, what about the actual relativistic distorted wave? In other words, calculating the distorted waves themselves, doing the integration of the T matrix. Well, again, this could be run on a PC in a few minutes. So in that sense, it's really quite a minor computational effort. That's for one transition. So if you want to do 10 transitions or 32 transitions, whatever, it's going to take you longer. But again, it's not all that difficult to do. So there's considerable scope for undertaking more elaborate calculations here, either in the bound state or in the distorted wave, if you want to do anything more elaborate than what we've got. So finally, just in case you're interested, here's the references for the experiment. Here's the reference for the integration in the complex plane. Here's the reference for the form of the integral form of the Dirac equation. So if you're interested, you can look at those. Thank you.